Hi everyone, my name is Ana-Andreea and I'm a fourth year PhD student at Columbia University. I'm really excited to talk to you today about our work on minimizing margin of victory for fair political and educational districting. This is work done jointly with my collaborators Avignan Chakraborty, Palash Dey, and Krishna Kumari from Max Planck Institute for Software Systems and the Indian Institute of Technology, Kharagpur. So the main premise of our work is, if you have a central planner, how do you divide people into groups given different purposes? And the purposes can include political purposes in electoral districting, educational ones for school districts, or administrative purposes when you want to divide people into departments, into offices, and so on. In particular, in the US, electoral districts and school districts are really important for voting scenarios as well as people's matching programs, students matching programs into schools. So it really matters who is in these groups, however, since groups can be quite unequal depending on their demographics or on their preferences. And the different divisions into different groups can have ramifications. The problem that we're tackling here is exactly that, bias in grouping. And this can have applications in gerrymandering scenarios, as well as in tackling diversity in schools, in teams, in departments, and so on, based on people's demographics. In particular, in the US, schools are heavily segregated, especially in New York City. And this can have real ramifications since non-white school districts actually get up to $23 billion less in funding than white districts. And this is despite serving the same number of students. So how do we tackle this problem? Our approach is to use the concept of margin of victory from computational social choice and minimize it. We can apply this concept whether we are in scenarios of political districting where people vote for candidates, or we're working with segregated networks in which people prefer, to say so, their demographics. So we model the segregation scenarios in the same form as a plurality election. The margin of victory is simply the number of votes needed to change in order to change the election outcome. Formally, in plurality election is simply the ceiling of half the difference between the plurality scores of the first two contenders. In this case, A and B are the top two contenders. Why are we using margin of victory for this case? There are several reasons for that. First of all, in unequal settings in which you have communities of different sizes, in which some may be more dominant, it can prevent monopolistic advantage and practices like packing. Because of that, it can empower a minority and create competition in these unequal settings. So you may ask, why not proportional representation in that case? Well, proportional representation is quite difficult to apply both in theory and in practice, and it may not be the best choice in certain scenarios. So for packing and cracking cases, it might not be the best. For example, if you're cracking a minority into different districts, keeping the same proportion as in their general population, you may actually not allow them to win any district, while minimizing margin of victory may still give them the option to win a few of them. Now, with this in mind, our problem setup is the following. We start with an initial partition. And imagine you have groups with people of different demographics or preferences for different candidates. You can imagine that the colors represent the parties for which people vote for or other features that they have. And the margin of victory of the first group is simply 1. You need one person to change their label. In this case, a person who's orange needs to change to green or to blue in order to change the election outcome. Similarly, the margin of victory in the second group is 2, and in the third one is 1. What we're aiming to do is to first formalize this problem. So on a theoretical level, the problem that we're solving is simply to minimize the margin of victory in these groups from this initial partition, starting from this initial partition, and computing whether such a scenario actually exists. We can either minimize the sum of margin of victories or the maximal one. Either case, in this case, we're looking at the bounded version of it. So if you don't have any constraints or on where people can move, we define this problem as fair regrouping, and the X simply comes from the fact that there's no constraints. This problem computes whether a solution exists with bounded margin of victory, and it does have an implicit constraint on the group size. Now, in many settings, people actually cannot move very far away, or you cannot redraw boundaries of districts in a very unnatural way. So you may define mobility constraints as the ferry grouping problem, and that simply entails having a list of where people can actually move. In other scenarios, you may have social network constraints where people are connected to each other, and we define this problem as fair connected regrouping. And in this scenario, you can imagine that you do not want to disconnect the groups by moving people and minimizing margin of victory. And that can be a scenario in which you do not want to disconnect a community. So with this setup in mind, we look at the theoretical complexity of our problems, and we notice that they are quite difficult. So except for the problem that has no constraints, which is polynomial time solvable if the number of groups is a constant, the other two problems are NP complete. Even with 3 candidates in the first case for fair regrouping, and even with 2 candidates in 2 groups for the social network constraints. For more general constraints, for example, in fair regrouping X, if the number of groups is not a constant, the problem is actually open. But given the complexity of this problem, we develop fast algorithms to approximate them and to solve it. So the greedy heuristics that we define basically take an initial partition and greedily move people from one group to another in order to minimize margin of victory. So in the scenario that you saw before, a greedy algorithm would simply choose, for example, a person of an orange label from the first group and move it to the second group, reducing its margin of victory from 2 to 1. We can reduce the total margin of victory or the maximum margin of victory, and we obtain similar results. So we define 3 different greedy heuristics that are based on the different constraints that we have. For no constraints, having mobility constraints, and the social network constraints that I mentioned before. And we test these greedy heuristics on both synthetic data and real data. So let's see how they perform. In synthetic data, we simulate networks based on the Ardashrini model, in which we also incorporate homophily. And this is based on several previous models that show that people who are similar actually connect more to each other. This basically establishes the unequal network setup that we had in mind, in which you have dominant communities and minority communities, and the dominant one are actually more interconnected or equivalently segregated. So, we simulate preferences for candidates, and again, in this case, that can be applied to political candidates or to preferences towards people's features or demographics. And we see that the greedy heuristics actually fastly reduce the margin of victory. We compare them to a baseline depicted here in gray, which is the optimal margin of victory that we can obtain. And you see in the blue lines that all of the greedy heuristics are able to reduce the margin of victory. You can also notice that the fewer constraints that they have, the more they can actually reduce the margin of victory. So in light blue is greedy regrouping X that has no constraints except for the group sizes, while in darker blue there is greedy connected that has the social network constraints. We also test this on real data. So we collect data from political constituencies in the UK, which means choosing 10 constituencies from the 2017 parliamentary election. And we choose them around Edinburgh, which is a region in which there are neighboring constituencies with very different election outcomes, in which people actually segregate quite heavily depending on what party they vote for. We also choose a set of schools in Detroit, Michigan, which is an area with very high segregation, and for which school districts are also racially segregated. We have the demographic information from Department of Education website from the schools, and we test our algorithms on them as well. So, what we see in real data is that the greedy algorithms are able to fastly reduce the margin of victory, both in the UK data and in the school data. On the left-hand side, you see the UK data, on the right-hand and on the right, the school data. And on the top is the maximum margin of victory being reduced, and on the bottom is the total. So, the darker blue represents the initial margin of victory, and you see that both lighter blue algorithms are able to reduce it greatly, especially for the UK data. We don't test the greedy connected algorithm due to lacking the social network information, which is something we hope to do for future work when such data is available. And to see actually the effect of these greedy algorithms on the different demographics, let's take a look at a few of the constituencies in the UK. On these are East Lothian, Edinburgh East, and Mid Lothian. On the left-hand side of each figure, you see the initial distribution of voters, and on the right, you see the distribution of voters after a greedy algorithm, after greedy regrouping. So, as you can see, in all of them, it reduces the margin of victory, and it's basically helping one of the minorities attain a higher representation. The more stark effect is looking at the demographic changes in schools in Detroit, Michigan. For example, in Dove Academy, Universal Academy, and the Cesar Chavez School, in which on the left side we see again the initial distribution by race, and we see that each of these schools is heavily segregated, so one race is actually extremely predominant. And on the right side, we see the racial distribution after greedy regrouping is applied. So, as you can see, that by minimizing the margin of victory in this scenario, we get to more equal representation of races, even if it's the top two. In cases in which we want to have a better representation of all races, certain additional constraints ought to be imposed on this problem. So the last thing I want to mention is that this greedy algorithms and this concept actually is reflective of the busing policies that were introduced in the US to alleviate school segregation. And in those policies, the point was that the government was providing different buses in order to move students from one school to another in order to encourage mixing. And unfortunately, those policies at the time were not received very well, but we're able to show that with this kind of concepts and algorithms in mind, they are not hard to implement, and they can be quite effective. So the key takeaways is that minimizing margin of victory can help, especially in very biased networks, by preventing monopolistic advantage in elections and helping in segregating scenarios in schools, in neighborhoods, and so on. There are many extensions that we can think of, from extending our theoretical results for different general cases and applying this methodology for scenarios like gerrymandering prevention. So thank you very much. That's all I had for today, and I'm looking forward for your questions.